when DPDK didn't even exist, was in touch with Intel, with Polmo drivers and other projects to find out how to accelerate packet capture. And it's a pleasure to see that today, everybody's talking about the next version of DPDK. So it seems that the problem has been solved. But today I'm not going to talk about DPDK per se. I'm going to talk about an application that is doing the packet inspection that you can use from DPDK. Okay. Doesn't seem to work. Okay. Why the packet inspection? Because I'm a software developer, so we develop a software application for network traffic monitoring. So we need to know what is happening in our traffic, because based on the traffic that we receive, so we have to do some actions. So for instance, to drop unwanted traffic, this is a typical example, or to characterize the traffic so people that are looking at our graph don't simply know that it's port 80 and TCP, but know that it's HTTP or is Amazon, AWS communication, something like that. So the way to classify traffic are many, okay? So the very old one is the UDP and TCP-based port classification. And then there is the QoS-based classification with DSCP, so you look at the flags inside the IP packets. There is statistical classification, and then there is the packet inspection. I'm now going to talk about this packet inspection, maybe if this button works. Not really. Can you help? Okay. So the port-based classification is very simple. You simply have a list of protocol and ports, and you say TCP 80 is HTTP. Obviously, this used to work very well years ago, but today is basically useless, because first of all, you cannot assume that over port 80 TCP there is HTTP traffic, and you also cannot assume that HTTP is only on that port. So it means that your assumption will be totally wrong. The QoS markers are still used today, but they're mostly used on routers when you want to give priority to traffic, so you want a device to basically to respect the quality markers that you have set with other means. So this is not what we want. There are too few. Thank you. The statistical classification is an interesting branch. It was very popular about 5-10 years ago. So the idea is very simple. Is to use techniques such as machine learning to apply to traffic. So in essence, you have examples of traffic. You say, this is HTTP, this is Skype, this is WhatsApp, and you train a system, and the system will learn that traffic pattern and give you a yes or no, or a score. And based on the threshold you set, you decide whether this is this traffic or another traffic. The problem of this approach is that the protocols have to be very different. You cannot have very similar traffic patterns. And also that it's very hard to extract metadata, because metadata extraction is one of the important things. I will show you later that saying that this is HTTP or saying that this is SSL doesn't mean much today. So you want to know exactly what type of protocol is behind that thing. And then there is this packet inspection. So in essence, we have to inspect the packet payload. So somebody has received the traffic, and this library I'm going to talk about today is about inspecting the traffic payload and deciding whether this is protocol 1 or protocol 2. Okay? So this is the idea. When today I say protocol, I don't mean the protocol RFCs. So I mean something more than that, application protocols. So for instance, inside the NDPI library, Facebook is a protocol. But Facebook per se does not exist. It's simply DNS or HTTPS traffic or Facebook 0, that this is a real protocol that are traveling towards Facebook, okay? So please, this is the only problem. So in traffic monitoring, it is important to understand the application protocol because we can give priority to certain traffic and stop other unwanted traffic. So it is important to inspect the traffic. Many people are asking me the same question, but how can you deal with encrypted traffic? Encrypted traffic is very popular today, and I assume it will be even more popular in the future. Actually, I hope that most of the traffic, if not all, will be encrypted. So it is important to understand from the traffic flow, the application protocol, but not to grab data from the stream. So our goal is not to decode the traffic. This is what I want to be very clear about that. But I want to know if this protocol is Google Mail or if this protocol is Facebook. So this is the important thing. And especially with the cloud, so with everybody going to the same place, it is very important to understand and to inspect the traffic. I want to give you an example. If you look at Spotify traffic, Spotify in our library is a protocol. But in essence, it's traffic going to the Google CDN, okay, that is used by Spotify, the application, for listening to music. So this is the important thing. So we want to know from our application whether this is music or this is something else. This is the idea. So in 2012, I decided it was time to create a truly open source library that was able to do DPI. The problem with DPI is that for some reason, it's still black art or is something magic. Toolkits are super expensive, so even if you want to approach a vendor of a DPI toolkit and talk about that, so you have to sign an NDA just to figure out what is the toolkit is doing, not for looking at the code or looking at the library. They're closed source, so it means that you must be happy of the protocol that they have, but if you want to add another protocol, probably you have to ask the vendor to add the protocol. And this sometimes is a problem. It's a problem because, first of all, it's a problem of freedom. So years ago, an application that didn't exist until that time, so when it became very popular, so the Pokemon Go, and everybody wanted to understand how much Pokemon Go traffic was on that network. So if you have to ask to a vendor, so to create a dissector for that, so put in the library, update everything, it's very complicated and it's very expensive. So instead, we created that in a couple of hours. So it is very important that. And second, we are looking at the packet payload, because here most of the people are probably looking at the header. So you want to see, this is my traffic, has to be diverted here. But here we are inspecting traffic. So it's about privacy. And I believe that open source is even more important here because we want to give people the ability to understand what is the library is doing with the packet payload, even though it's encrypted. In case of NDPI, it's a library that divides the protocol in two families, so major and minor protocol. So in the case of, for instance, YouTube upload, so it means that somebody is sending to YouTube a video, so it's uploading the video on YouTube. You will see QUIC, that is the network protocol, and then YouTube upload is the application protocol. So we are trying to combine the network traffic with the application protocol. So QUIC will stay for a while, I assume, whereas those protocols, those application protocols, the one in green, can change very often. Especially are changing those protocols that are not specified anywhere. A typical example is WhatsApp. The WhatsApp as a protocol does not exist, but it exists in terms of application. So if you want to, let's say, stop WhatsApp during a conference like this, so people can look at me instead of doing messaging, it's very important that over time you update the dissector. Actually, this is what we do. Simply because the protocol itself is changing. It's changing very often. And as you can see, this is a typical example. Most of the protocols today are just QUIC and SSL and HTTP-based, mostly QUIC and SSL. And then you will see a pattern. So if you say, if this SSL traffic going to whatever.netflix.com, then it is Netflix, something like that. So this is why the number of protocols or real network protocols are not that many, so actually are decreasing, because people are trying to reuse, always the same protocols and then put some logic on top of it. So in this case, we are dissecting the server name indication to figure out whether this is Netflix or not. But because the protocols are many, and if you talk with a DPI vendor, they will always say, hey, I have 1,000 protocols, I have 2,000 protocols, 3,000 protocols. This is not a bonus, because even myself, that I'm developing the library, I don't know all the protocols. I use them from time to time, but I'm not familiar with them. I don't remember after some weeks. So it's important to classify in clusters, especially because if there are people that are using that for preventing people from doing things like today. Okay, so disable text messaging, for instance, until the conference ends. So I want to say, I want to have this category off. Okay? I don't want to know all the protocols, because if I tell to my mother what is peer-to-peer or what is a social network, she knows a little bit about that, but she doesn't know all the specific protocols. That's why we decide to cluster them into categories, so that, first of all, they're easier to be represented, so you give people the idea of what the users are doing, And then you give also the possibility of configuring very easily the application. So if you want to prioritize traffic, let's say interactive video, a lot of bandwidth, YouTube upload, less bandwidth, because it's not as important as watching the video itself. So inside the PI, basically, we dissect the traffic based on flows. And a flow is a 5-tuple plus VLAN. And then whenever we have a flow, so we pass, and I will show you some example later on, we pass this packet payload to the library, and the library will predict what is the protocol, okay? The classification is very simple. First of all, we have to start from a protocol that will likely match the traffic. So for instance, if I see TCP on port 80, it's probably a best idea to start with the HTTP dissector, okay? Because I can start with SMTP, but it's very unlikely that over port 80 SMTP runs, even though it can be the case. So NDPI is trying to use the most likely dissector to be used on that traffic flow, and it iterates. So we give, every time we receive a packet to NDPI, NDPI will say, okay, I don't know, at some point you have to give up. Okay, because if after a few attempts, the library is not able to understand what is the protocol, it means that the library will not be able to understand. This for a few reasons. First of all, because in order to classify the traffic, we must see the traffic from the very beginning. So usually, the most important information is at the beginning, since in ACK, and then if you have SSL, the SSL negotiation. So if you are in the middle of a flow, it's unlikely that even if you continue dissecting, you will find out something. But there are some exceptions. Let's talk about WhatsApp, or let's talk about Skype. These are the typical example of protocols that misbehave, let's say. In order to pass through firewalls, okay, at the beginning of the communication, they look like a protocol, and after a while, they become something else, okay? So the library, first of all, doesn't have to report immediately, this is protocol X, but the library has to say, okay, this looks like this protocol, but if you have more packets, I will improve my classification, because I don't want to tell you that this is voice, but I want to tell you that this is Skype voice, okay? So depending on the traffic, the library will improve the classification simply because those protocols are misbehaving. Again, they are not real protocols. They are simply doing that because they want to pass through firewalls, and as soon as they pass through the firewall, they become something else. So the classification life cycles works interactively. I will show you an example. So in essence, there is DPDK at the bottom. The library is not is neutral from the packet capture point of view. So somebody has to capture the packet, is sending it to the library. The library is trying to predict the protocol, and then we report the protocol information to the application. The application can do something with this information. So like I've said, we have to, first of all, to identify what is a flow. A flow is a packet, okay, that has a 5-tuple plus 1, usually with the VLAN property. So as soon as there is a new flow, a memory for the flow has to be allocated, and then the packet is passed to the library with the flow information. And then the library will report, okay, unknown, or we report this is the protocol. So a typical example is SNMP or UDP-based protocol like DNS. So with one packet, you can figure out what is the application protocol. If you have SSL or QUIC-based application, then it will take a few packets until you can say, this is the protocol. So if you are happy of SSL, that's enough. But there are some protocols that at the beginning look like a good protocol, and then later on they change. So I suggest that even if you have a protocol that is very simple, like HTTP, don't wait until you see get/, but also look at the response. So that's why I think a few packets have to be sent to the library in order to have a reliable classification. And then another important thing to be taken into account, because here you are familiar with millions of packets per second, this type of metrics, that the performance of the packet inspection depends on two things. First of all, on the speed you can capture the traffic. And second, on the number of flows, number of concurrent flows. First of all, because you have to remember that when you receive a packet, you have to remember the flow it belongs to. So we have some memory issues here. And also another point is that the more these sectors you have, okay, the slower will be the library. Because if you just want to find out is this Skype or not, it's very easy. But if you have 200 or 1,000 protocols, it's a bit more complicated to do that. Even though today, like I've said, the number of protocols, real protocols we see on the network are probably 20. And what we call protocols are just usage of those protocols for different purposes. So don't think that million packet per second or packet capture is the only metric. This is very important, again, but it's one of the important metrics for DPI. Inside the NDPI, so there are examples that allow you to use it from the PDK. So for instance, we have this simple application called NDPI Reader that is able to read from pickup, from other sources, or from the PDK. So you can take this application, you can connect it to a network, you can receive packets, and the library is predicting the application protocol is printing that on the screen as part of the application. So if you look at the application itself, you will see that in essence there is one line of code that you have to add to your application. So when you have the packet payload, you have to pass the packet payload to the library, and the library will predict the protocol. And in return, the library will say unknown, or will say this is the protocol X, and you're done. And once you have the application protocol, you have to remember that all those packets belonging to that flow will share the same application protocol. And you probably have to do something. Let's make an example. We have people that have integrated NDPI inside the low-cost routers with the IP tables. So a typical thing is that they use the prediction of NDPI to set the marker into IP table so that IP table will honor that marker and will drop or have full speed or decrease the speed with the traffic controller of the packets belonging to that flow. Another typical example is this one, that is basically FWD, that is part of the PDK. So you simply have to add a few lines of code inside the red part, and everything else will be the same. So in essence, you have to pass the packet to the library. So what we have to do, in essence, is on top of the PDK, we have to create a hash table, and we have to remember, based on the 5 tuple, what is the flow to which the packet that has been received belongs to. So we have to create a hash table. So we have created a small library called pfringft flow table that is able to do that. But if you have an existing application, I believe that you already have an hash table. So you simply to remember inside the hash table for the bucket that corresponds to the packet, you have to allocate some memory that will be used by NDPI for predicting the protocol. And as soon as the protocol is predicted, so you simply have to remember the protocol prediction, and you can delete that memory. We are talking about a few kilobytes. I will show you later. So inside this library, you can put some callbacks. You can say, call me whenever a new flow is created, a new flow is deleted, or every time a packet is processed. But again, I assume that most of you, that those who want to add the packet inspection to the application, we already have this data structure. So you simply have to add extra information for keeping this thing in memory. I want to show you some examples of usage of the library. So the one on the left shows you how to create, in essence, a bump in the wire. So this is a typical example of some network operators that, for some reason, they have to predict some specific traffic application to flow, or because they want people to pay for traffic, and they want to ban, for instance, application like Skype. Let's give an example, so people can have to use the phone, and they can make some money. So in this case, basically, you create a bridge. Okay, there are many examples inside DPDK. You create an hash table. You remember on each bucket the flow to which a received packet belongs to, and you call the DPI library, and DPI library will tell you the application protocol. And as soon as you have made a prediction, you have to go and look at the rules if that protocol can pass or not pass. The point is that, as you have realized, it's not possible to say with one packet, okay, 100%, this is the application protocol, because it depends on the packet itself. Again, if you have UDP-based traffic, it is very likely with one packet you can predict. Otherwise, if you have standard traffic, and you cannot rely on other sources of information, like the IP address, for instance, you must let people speak a little bit, and then as soon as you realize that this is the protocol that you cannot allow people to use on your network, then you have to stop. So it means that with DPI, you cannot prevent from people doing a little exchange of traffic until you stop them. Okay? So this is very important. It's not like with access control list that you say yes or no immediately. Here depends on the traffic. Another example is Suricata, that is an IDS, or it can be applied to Bro. For instance, we have other examples for Bro or for other popular intrusion detection systems. So that allows basically NDPI to say, don't send Suricata traffic that is not necessary, because all those applications are CPU bound. So in essence, they are doing a lot of work just to figure out whether certain traffic is good or bad from the security standpoint. But Suricata, for instance, usually will not find anything bad in Netflix traffic or YouTube traffic. So if you look at the way traffic is distributed in modern networks, you will see that 2/3 of the traffic are those applications that are not very important for security, because we assume that Facebook, Google, and these guys are doing a good job. So we have to focus on the remaining part of the traffic. So a good way of accelerating this type of application is to reduce the workload. How? Simply don't send in those applications the traffic that they will not be interested in. So simply filtering the traffic at the bottom layer. And so this is a typical example where NDPI can be used for doing that. Just to give you some performance figures, so this is an example with a low-end Intel system. So you can see that with one core, we can do about 10 gigabit. I'm talking about real traffic, okay? I will show you later some slides where we say 64 bytes packet, but this is not real traffic, because with DPI, we have to play with real traffic, okay? So as you can see, it is pretty efficient. The memory that is used here, so we have a huge number of flows, is big because we have many flows, but per flow, you will have 2 kilobytes. So with 2 kilobytes, you have enough memory for letting NDPI to work. And as soon as NDPI has predicted the protocol, you can delete that memory, and you can keep simply the application protocol, so 2 16-bit integers or a 32-bit. So the performance, I believe, is very good. And so this is another slide that is talking about the same problem, so predicting traffic with a more performant application we have developed called mProbe CentOS. So in this case, I want to give you a few scenarios. So the first one is a typical example where we have synthetic traffic that 64-byte packet doesn't mean much. And then in the other example with an FPGA, so I give you other figures of traffic, real traffic that is sent, in average is 1 kilobyte packets that is sent to the library, and the library has to predict. Remember that the library will be affecting your traffic only at the very beginning, because you have to send the library only the first few packets of a communication. Because as soon as the library has predicted the protocol, the library will not be longer useful to you, because you have the protocol, okay? So this means that those numbers are affected by the number of flows that you have. Let's say it again. If you have one flow, okay, of 100 gigabit, the library will look at the first few packets, 8, I've said, of the communication, and then everything else will not be affected. If you have those 100 gigabit link full with millions of flows, so each flow has to go through the library, because you have to analyze the first few packets of the library, okay? So the application performance I put on this slide is just to give you an idea of what you can expect. But the real application performance depends on the nature of the traffic. So in this case, packet capture is an important component, but if you want to create a data sheet of your application, it's very important to understand how many concurrent flows you have, okay? Because, again, the library is only affecting the first few packets of the flow. As soon as the flow has been predicted, the performance will be, as without the library. Another important thing that I want to say is to tell you how the library is matching the sub-protocols. So like I said before in one of the few slides, Netflix. So SSL, Netflix. So inside NDPI, we have a Hauck-Eurasic-based algorithm that is doing that. So we do substring searching. So whenever we are able to decode the server name indication inside the QUIC or SSL or inside the URL HTTP, we are going to match this with HowCoreSIG. But Intel has also created a new library called Hyperscan. So if you go to Hyperscan.io, you will find the library. That is very fast. In this example, you will see that it's slightly faster than our library. But there is a big difference. Here, with HowCoreSIG, we can do only substring search. So you can say, find this string inside the server name indication or inside the URL. Many times is enough. But with Hyperscan, like you have seen, it's a little bit faster. So even though it's doing much more than that, with Hyperscan, you can have regular expressions. So you can search something inside the traffic. Because if you want to stop nasty traffic, there are many websites that start with blah, 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 Facebook, blah, 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 something else, okay? If people look, oh, Facebook, I've seen the Facebook in the URL, it's Facebook. It looks like Facebook, but it is not Facebook. So with those type of cases, Hyperscan will be great because you are able to say it has to end with facebook.com, okay? Facebook cannot be anywhere in the server name indication. With the substring search, we cannot do that. So the library itself, Hyperscan, is faster, and is able to do that. Otherwise, we have to do HowCoreSIG, and we have to do manually. So let's say we have some routine inside NDPI that are able to figure out if this problem is really like that, because this is a very important thing. And I forgot to say that inside the NDPI, you can load on demand or at startup several new strings so that you can create additional protocols on demand or categories. So some people created some papers. So these are a typical example. So I've been created 5 years ago, so it's a little bit outdated. Just to tell you that even though it's open source, so people sometimes think that open source is not high quality. I mean, it was able to match the expected performance. Actually, it was much better than all the other toolkits that they have been evaluated. So just to wrap up, I've shown you today that it's possible to do DPI with an open source library. So DPI means problems because, like I've said before, you have to sign an NDA, there is a vendor lock problem, and so on. Here, it's open source, it's free of charge, and also it's open. The fact that it's open is very important because you can look at what the library is doing with your payload. That's very important from a point of view. It is fast. It's able to match with one core 10 gigabit performance. It will be used only at the beginning of the communication. So don't be afraid. It's not that you have to slow down everything. So simply at the beginning of the communication, so the library has to predict the protocol. So as soon as the protocol has been predicted, you know that this is the protocol, so everything will work at the performance that you're familiar with. It's available, it's open source, so it's on GitHub, the code. It's maintained by a community. And I encourage you to test it. We have created and we have added support for the PDK, so you can have applications that are able to read packet from the PDK to demonstrate you how to do that and pass it to NDPI. You can create a passive application, so read the traffic, or also active applications, so a bump in the wire that allow you to stop unwanted traffic communication. And then finally, let me say thank you to Intel that sponsor NDPI, and they like what we are doing. We'll do our best to be part of this community. Thank you very much.
Thank you. I think we have just time for one question. If you have, or
please.
Yep.
So when you inspect those packets, right? Occasionally you would have two different protocols then mixed up in one packet. Would you have a situation like that? How would you decouple them and not dropping?
Make an example of those protocols, just to understand.
Yeah. So multiple protocols presented in one packet.
So if you're saying that with one packet you can figure out the protocols like DNS?
So for example, right, you one packet, you might have the WhatsApp message, some other HTTP message.
No, with WhatsApp you need many more messages.
Yeah.
So you have to remember the flow. So inside your hash table, you have to pass the flow to NDPI. NDPI will keep some memory just to remember the history, and then will predict the protocol. because most of the protocols are not, cannot be predicted with one packet.
Yeah. So for example, when we detect something, you don't like that packet, you want to drop it, you want to bust that packet, right? But you don't want to drop the rest. So what would you do? How would you handle that situation?
For dropping packet, I said, I mean, I'm Italian, but you don't know if I speak Italian unless we speak a little bit of Italian. So we have to start speaking. So the first few packets have to pass. And as soon as you realize that I can speak Italian and you don't like Italian, so you can drop it. But the first few packets have to pass. It's not ACL and ICL that you say IPM port and everything you need is inside the packet header. With DPI, you have to let traffic go through until the library, for instance, sees the server name indication if you're talking about SSL.
Okay, all right, thank you.
Thank you.
Great, thanks. Thank you.
Thank you.